Hello everyone. Today we'll study section 11.4, tension plane. What's a tension plane? Before we study what's a tension plane, let's review what's a tension line first. What's a tension line? Let f of x be a function and let assume its graph looks like this. Assume that's the graph y equal to f of x. Assume that's its graph. Assume that's its graph. Let P be a point on the line. Let P be a point on the line. How do we define a tension line at P? How do we define a tension line at P? So, to find a tension line at P, we try to zoom in at point P. Assume that's a smooth curve. Assume this is a smooth curve. To find a tension line, let's try to zoom in at P. If I zoom in, toward the point P, I have a curve looks like this. That looks much straight than the original graph. That looks much straighter than the original graph. If I keep zooming in, if I zoom in again, toward point P, we can see that this line tends to a straight line. So if we keep zooming in toward point P, we can see that the graph tends to a straight line. If we keep zooming in, we can see that the graph tends to a straight line. And this straight line is called a tension line at P. And this straight line is called the tension line of f of x at P. Similarly, for the tension plane, we let f of sy be a two variable function. Let f of sy be a two variable function. Let's sketch the graph. Assume it's a smooth curve. Assume it's a smooth surface. Let's sketch the graph. Assume it's a smooth surface. For example, it looks like this. Assume it's a smooth curved surface. Let P be a point on the surface. Let f of sy be a two-variable function. Let P be a point on the surface. Now, same thing. If we zoom in toward P, if we zoom in toward P, if we zoom in here toward P, if you zoom in toward P, you can see that the surface becomes flatter. If you zoom in toward P, the surface will become flatter. If you could keep zooming in, you can see that the plane will eventually tend to a flat plane. If you keep zooming in toward point P, the plane tends to a flat plane, and this flat plane is called a tension plane. So for tension plane, we define it in the following way. In the graph of z equal to f of sy, let P be a point on a smooth surface. If we keep zooming in toward point P, the surface tends toward a flat plane. And this flat plane is called the tension plane of f of sy at point P. Now, my next question is, if I know a function, I know a point P on the graph of the function, how do I find the tension plane at point P? How do I find tension plane at point P? If I can find two vectors that lie on the plane, then by taking cross product, I can find the normal vector. Using normal vector and point P, I can find the tension plane. So next, I'll show you how to find two non-parallel vectors on the tension plane. Next, I'll show you how to find two non-parallel vectors on the tension plane. First of all, let's recall partial derivatives first. Let f of sy be a two-variable function. F sub x of AB represent the rate of change or the slope of tension line. At the plane and the cross section y equal to b at point A, comma b. F sub s of AB represents the slope of the tension line and the cross section y equal to b at point A, comma b. Let me show you the picture. It will make more sense to you. Suppose that's the graph z equal to f of sy. Say b is somewhere here. The cross section at y equal to b looks like this. Assume point A is here. That's the point A, B. That's f of AB on the graph. F sub x of AB represents the slope of the tension line and the cross section. That's the tension line and the cross section. That's the tension line and the cross section. F sub x of AB represents the slope of this tension line. Now, if I zoom in toward a point f of AB, if I keep zooming in toward a point f of AB, the surface will tend to a flat plane. If I keep zooming in toward f of AB, the surface will tend to a flat plane. And the cross section, the curve on the cross section tends to a straight line. If I keep zooming in toward a point f of AB, the surface will tend to a flat plane, and the cross section, the curve on the cross section tends to a straight line. So by the definition of tension plane, if we zoom in toward f of AB, the surface tends to a flat plane. This flat plane is the tension plane. And similarly, at f of AB, if I keep zooming in, the curve tends to a straight line. This curve is called a tension line at f of AB. So we can say that at the point AB, the tension line in the cross section y equal to B lies on the tension plane. Similarly, at point AB, the tension line in the cross section x equal to A also lies on the tension plane. Let me show you the graph. Let's draw the cross section at s equal to A. S equal to A is somewhere here. S equal to A. The cross section at s equal to A is somewhere here. That's in the cross section at s equal to A. And that's the tension line in the cross section s equal to A. That's the tension line in the cross section y equal to B. That's the tension line in the cross section s equal to A. So if we zoom in at this point, the other tension line also lies on the tension plane. If we zoom in, the other tension line also lies at the tension plane. Next, let's take a little time to review slope. What does slope of a line means? Slope of a line M represents change of y over change of x. What does it mean? For example, when slope is 2, what does it mean? 2 can be rewritten as 2 over 1. That means when change of x is 1, change of y equal to 2. Similarly, what does slope of, for example, 3.25 means? 3.25 can be rewritten as 3.25 over 1. That means when change of x is 1, change of y is 3.25. Do you remember how is slope related to derivative? Let f of x be a function. Assume its graph looks like this. Let A be a point on the x-axis. F prime of A, what does it mean? What does f prime of A mean? F prime of A represents the slope of tension line at point A. F prime of A represents the slope of tension line at point A. That means dy over dx, change of y over change of x. F prime of A represents dy over dx at point A. For example, what does it mean? For example, when f prime of A equal to 2, what does it mean? That means when change of x is 1, change of y is 2. 2 can be written as 2 over 1. What does f prime of, if f prime of A equal to, for example, 3.25. That means at point A, if change of x is 1, change of y is 3.25. So in general, at point A, at point s equal to A, at s equal to A, if change of x is 1, then change of y is f prime of A. If change of x is 1, change of y is f prime of A. If change of x is 1, change of y is f prime of A. So when change of x is 1, change of y is f prime of A. So when change of x is 1, change of y is f prime of A. So the vector, can we see that the vector 1 comma f prime of A lies on the tangent line. The vector, this vector 1 comma f prime of A, 1 comma f prime of A lies on the tangent line. Keep this idea in mind. Next, let's take a look on the partial derivatives. For the partial derivative, f sub s of AB represents slope of tangent line and the cross section y equal to b. F sub x represents slope of this line. At this line, the slope represents change of z over change of x. Y is a constant. And at this cross section, y is a constant. This slope represents change of z over change of x. Change of z over change of x. So there's no change in y direction. If the change in x direction is 1, then change in z direction will be f sub x of a b. This is a vector lies on the tangent line. Similarly, for f sub y, f sub y represents slope of tangent line at the cross section s equal to a. For this line, for the slope of this line, of this tangent line, x is a constant. There's no change in x direction. When change of y is 1, change of z will be the derivative. There's no change in x direction. When change of y is 1, change of z will be f sub y of a b. So this vector lies on the tangent line. First vector lies on the tangent line and the cross section y equal to b. That's a tangent line lies on the cross section. That's a vector lies on the tangent line and the cross section s equal to a. So since this vector lies on the tangent line and both tangent line lies on the cross, both tangent line lies on the tangent plane, then I can say these two vectors lie on the tangent plane. since both tension lines lie on the tension plane at the point A, B, then vectors 1, 0, f sub x of A, B, and vectors 0, 1, f sub y of A, B. Then these two vectors are vectors lie on the tension plane. Since both tension lines lie on the tension plane, and these two vectors lie on the tension lines, so these two vectors actually lie on the tension plane. Now we have enough information to derive the equation of the tension plane. Let f of sy be a two-variable function and let x0, y0, z0 be a point on its graph, on the graph of z equal to f of sy. Two vectors on the tension plane is that v1 equal to 1, 0, f sub x of x0, y0. v2 equal to 0, 1, f sub y of x0, y0 that we just found, two vectors on the tension plane. Then once I know two vectors, I can find the normal vector. Once I know two vectors on the plane, I can do cross product and find a normal vector. Cross product, normal vector n equal to v1 cross v2. Do cross product, we have I, j, k, 1, 0, f sub x, 0, 1, f sub y. Take determinant, that's I times 0, f sub x, 1, f sub y, minus j times 1, f sub x, 0, f sub y, plus k times 1, 0, 0, 1. Then take determinant. I have 0 minus f sub x, f sub y minus 0, but it's negative. 1 minus 0 is 1. So that's the normal vector. Once I know the normal vector, I know a point on the plane, I can use the equation of a plane to find the equation of the tension plane. Equation of plane is a x minus x0 plus b y minus y0 plus c times z minus z0, where a, b, c represent the component of the normal vector. x0, y0, z0 represent the component of a point, which is the same as what we have here. So I replace a, b, c with the component of the normal vector. I have negative f sub x of x0, y0 times x minus x0 minus f sub y of x0, y0 times y minus y0 plus 1 times z minus z0. Then to make it easier, I move these two negative terms to the right side. Move these two negative terms to the right side. I have z minus z0 equal to f sub x at x0, y0 times x minus x0 plus f sub y at x0, y0 times y minus y0. This is the equation of the tension plane. That's the equation of the tension plane. Sometimes there are too many x0, y0. Sometimes people write it like this. Z minus z0 equal to f sub x times x minus x0 plus f sub y times y minus y0. We assume we know we evaluate f sub x, f sub y at the point x0, y0. So this formula is looks a little shorter than this. Keep it in mind. Next, let's do some simple example about tension plane. Find the equation of the tension plane. At the given point. First example, we have f of sy equal to 2x squared plus y squared. Find the equation of tension plane at the point sy equal to 1, 1. Remember, the formula for tension plane is z minus z0 equal to f sub x at x0, y0 times x minus x0 plus f sub y at x0, y0 times y minus y0. So we first of all find, we know x0, we know y0, so we can find z0 first. To find z0, we know x0 is 1, y0 is also 1. To find z0, you plug in x and y, you can find z. If I plug in 1, I have 2 times 1 squared plus 1 squared, which is 3. So that's a point. Now we need to find the partial derivative. F sub x is, I take partial derivative with respect to x. I have 4x. Then evaluate at point x0, y0. Evaluate at point x0, y0, which is 4 times 1 equal to 4. F sub y, we take partial derivative with respect to y. I have 2y. Evaluate at the point x0, y0. I have 2 times 1 equal to 2. Then plugging, we have equation of tension line is z minus z0 equal to f sub x times x minus x0 plus f sub y times y minus y0. And usually we try to write a plane in the simplest form. Move variable to one side, constant to the other side. I have z minus 3 equal to 4x minus 4 plus 2y minus 2. If I simplify, I have 4x plus 2y minus z. That's negative 6. When I move over, become positive 6. Positive 6 plus negative 3 is positive 3. Then usually write x on the right side. We have 4x plus 2y minus z equal to 3. That's the equation of the tension plane. Another example, the f of sy equal to xexy. Find equation of tension plane at the point sy equal to 2, 0. First of all, find the point x0, y0, z0. x0 is 2. Y sub 0 is 0. For z sub 0, you plug in x and y. Find z. If I substitute x and y, I have 2 times e raised to 2 times 0. E raised to power 0 is 1. So my z0 is 2. That's my point, 2, 0, 2. Next, I take the partial derivative. F sub x, I take partial derivative with respect to x. Here, I have two functions of x, do product rule. Derivative of the first times the second plus the first times derivative of the second. I treat y as a constant. Then I evaluate this partial derivative at the point 2, 0. Substitute 2, 0 for s and y. E to the power 0 is 1. E to the power 0 is 1. X is 2. E to the power 0 is 1. Y is 0. So I get 1. Next, we find f sub y. Take partial derivative with respect to y. I treat x as constant. I have x times esy times x, which is x squared esy. Then substitute 2 for x, 0 for y. I have 2 squared times e to the power 0 is 1, which is 4. Then use the formula. Plug in the values. Z minus z0, z0 is 2, equal to f sub x times x minus x0 plus f sub y times y minus y sub 0. Then simplify. We have z minus 2 equal to x minus 2 plus 4y. That means x plus 4y minus z equal to, I move negative 2 over, I get 0. So the answer is 4x, no, x. The final answer is x plus 4y minus z equal to 0. Next, we will study linear approximation. For a single variable case, we try to use a line to approximate a function. That's called linear approximation for a single variable function. So we try to use the equation of line to approximate a function. Equation of line is y minus y0 equal to slope times x minus x0. At s equal to a, x0 will be a, and the slope will be f prime of a. The slope of tangent line is f prime of a. At s equal to a, your y0 will be f of a. You plug in a into the function. That's the equation of line. That's the equation of tangent line at s equal to a. Then to find a linear approximation, we get y by itself. Write it as L of x. Get y by itself. Get y by itself. We have f of a equal to f prime of a plus f prime of a times s minus a. And this is a function of x. We write it as L of x equal to f of a plus f prime of a times s minus a. That's the linear approximation for a single variable function. Now, For a two-variable function, we try to use a tangent plane to approximate a two-variable function. We try to use a tangent plane to approximate a two-variable function. So equation for tangent plane is z minus z0 equal to f sub x of x0, y0, x minus x0 plus f sub y of x0, y0, y minus y0. Let's try to find the tangent plane. Let's try to find a linear approximation at sy equal to ab. Let's try to find a linear approximation at the point s equal to a comma b. So I plug in a for x0, plug in b for y0. I have f sub x of a b x minus a plus f sub y of a b y minus b, and z0, for z0 I plug in a b into function f. I have f of a b. Z stays the same. That's the tangent line at sy equal to ab. So that's the tangent plane at the point sy equal to ab. Then if I isolate z, if I get z by itself, I have z equal to f of a comma b plus f sub x of a comma b s minus a plus f sub y of a comma b y minus b. That's the linear approximation for a two-variable function. That's the linear approximation for a two-variable function. Usually, this is a function of x and y. A, b are constant. This is a function of x and y. So I can write this z as L of sy. So keep this formula in mind. Now for a single variable function, L of x is f of a plus f prime of x minus a. For two variable function, L of sy is f of a b plus f sub x of a b s minus a, f sub y of a b y minus b. Similarly, we can guess the linear approximation for a three-variable function. It will be L of syz equal to f of abc, abc is a point, plus f sub x of abc x minus a, f sub y of a b c y minus b, plus f sub z of a b c z minus c. That's the formula for linear approximation. Keep it in mind. That's the formula. Those are the formula for linear approximation for single variable, two variable, three variable functions. Keep it in mind. Okay, let's do some simple example. Let's do some simple example here. Let f of sy equal to square root of 4 minus s squared minus y squared. Find a linear approximation at the point 1, 1 and use it to approximate (1.01, 0.97. So first step, we try to find f of AB, f sub x of AB, f sub y of AB. So let's find f of AB first. Here AB is 1, 1. So f of 1, 1 equal to square root of 4 minus 1 square minus 1 square, which is square root of 2. Then find the partial derivative with respect to x. I get half 4 minus x squared minus y squared raised to negative half times negative 2x. Take partial derivative with respect to x. Then I substitute 1 for x, substitute 1 for y. I have negative 1 times 1 over square root of 2, which is negative 1 over square root of 2. Next, for f sub y, take partial derivative with respect to y. I have half 4 minus x squared minus y squared raised to negative half times negative 2y. Then substitute 1, 1 for x and y. Substitute 1, 1, 1 and 1 for x and y. Half times negative 2y is negative 1. And plugging 1 and 1, I have 2 here. 2 raised to negative half is 1 over square root of 2. I also get negative 1 over square root of 2. Then plug into the formula. My L of sy equal to f of 1, 1, f sub x of AB. I plug in 1, 1 already. I have negative 1 over square root of 2. X minus a minus 1 over square root of 2, y minus b. That's a linear approximation. Now use it to approximate the point 1.01 and 0.97. I plug in 1.01 for x. I plug in 0.97 for y. When I use a linear approximation, I plug in 1.01 for x. I plug in 0.97 for y. I have L of 1.01 0.97 equal to square root of 2 minus 1 over radical 2 x minus 1 1.01 minus 1 minus 1 over radical 2 0.97 minus 1 and use your calculator. I get 101 over 100 times square root of 2. Next example, let f of xy equal to x squared minus sy plus half of y squared plus 3. Find a linear approximation at the point 3, 2 and use it to approximate f of 2.94 and 2.01. So we first of all find f of 3, 2 first, use the formula L of sy equal to f of a comma b plus f sub x of a comma b x minus a plus f sub y of a comma b y minus b. So we find f of ab first, which is f of 3, 2. F of 3, 2. I substitute 3 for x, substitute 2 for y. I get 3 squared minus 3 times 2 plus half times 2 squared plus 3. 3 squared is 9. 9 take away 6 is 3. 3 plus 3 is 6. 6 plus 2 is 8. Then we find the partial derivative f sub x. I take partial derivative with respect to x. I have 2x minus y. Then substitute 3 for x, substitute 2 for y. Find f sub s of ab. Substitute 3 for x, substitute 2 for y. I have 3 times 2 is 6 minus y. Y is 2. I get 4. Now I find f sub y. F sub y of ab. I take partial derivative with respect to y. I have negative x plus y with respect to x. With respect to y. Negative x plus y. Take partial derivative with respect to y. Then I substitute 3 for x, 2 for y. I have negative 3 plus 2, which is negative 1. Then plugging into the formula, L of sy is f of ab, that's number a, plus f sub x, that's 4, x minus a, plus f sub y, that's negative 1, times y minus b. B is 2. Then let's call a linear approximation. Then we use it to approximate 2.94, 2.01. I plug in 2.94 for x, 2.01 for y. I have a plus 4 times 2.94 minus 3 minus 1 times 2.01 minus 2, which is a plus 4 times negative 0.06 minus 1 times 0.01, which is a minus 0.24 minus 0.01, which is 7.75. Next, let's try a 3-variable case. Let's try a 3-variable case. Example 3. Let f of syz be the function y sine x plus 2yz. Find a linear approximation at the point 0, 1, 0 and use it to approximate f of 0.1, 1.04, negative 0.06, 0.1, 1.04, negative 0.06. So we first of all find f of 0, 1, 0. Let me put a formula here. The formula for 3-variable function is L of syz equal to f of abc plus f sub x of abc x minus a plus f sub y of abc y minus b plus f sub z of abc z minus c. So find f of ABC first, which is I substitute 0 for x, 1 for y, 0 for z. If I substitute 0 for x, first term becomes 0. If I substitute 0 for z, the third term becomes 0. I get 0. Then for f sub x, I take partial derivative with respect to x. It means I treat y as a constant, yz as constant. So this term becomes 0. This term becomes y cosine x. I take partial derivative with respect to x. Then substitute 0 for x, 1 for y. I get cosine 0 is 1, which is 1. For f sub y, I take partial derivative with respect to y. I get sine x plus 2z. Then substitute. I plug in 0 for x, 0 for z. I get 0. For f sub z, I take partial derivative with respect to z. I treat sy as constant, so first term becomes 0 when I take derivative. Third term becomes 2y. Then I substitute 1 for y, I get 2. Then use the formula L of syz f sub x f0 f of ABC is 0, f sub x is 1 minus times x minus 0 plus f sub y times y minus 1 plus f sub z times z minus 0. Then simplify. I have 1 times x minus 0, s minus 0 plus 2 times z minus 0. Then I substitute the point. L of 0.1 comma 1.04 comma negative 0.06. I have 1 times 0.1 plus 2 times negative 0.06, which is negative 0.12. Sorry, 0.02, negative 0.02. That's 0.1 times negative 0.12 become 0.02. Next, use the linear approximation to estimate the value of 2.92 raised to the power of 1.97. So if you want to use the linear approximation, you need to first of all guess a function in this format. So I first of all guess by guessing a function in this format. My f of sy is x to the power of y. Next, you guess the value for x and y. That's easier to be calculated. Guess the value for x and y, and that's easier to be calculated. I can guess my x value is 3, my y value is 2. For 3 and 2, they are very, very close. And if I use 3 and 2, that's very easy to be calculated. Next, I try to find a linear approximation. I find f of AB first. I find f of 3, 2. Plug in 3 for x, plug in 2 for y. I get 3 raised to power 2, which is 9. Next, I find a partial derivative with respect to x. Partial derivative with respect to x, that's y times x to the power of y minus 1. Then I plug in 3 for x, plug in 2 for y. I have 2 times 3 to the power 1. Plug in 2 for y, plug in 3 for x, which is 6. Next, for f sub y, take a derivative with respect to y. I have ln of x times x to the power y. Then I plug in 3 for x, plug in 2 for y. I have ln of 3 times 3 to the power 2. 3 to the power 2 is 9. So I have 9 times ln of 3. Then write down the formula for linear approximation. L of sy is f of ab plus f sub x times x minus a plus f sub y times y minus b. The formula is L of sy equal to f of a comma b f sub x of a b x minus a plus f sub y of a b y minus b. Then we plug into the formula. Next, let's estimate the value 2.92 times to the power of 1.997. I substitute 2.92 for x, 1.97 for y. I have 9 plus 6 times 2.92 minus 3. Plus 9 ln of 3 times y minus b. Y is 1.97. B is 2. Y is 1.97. Then I have 9 plus 6 times negative 0.08 plus 9 ln of 3 times negative 0.03. Then use your calculator for the rest. I got 8.2233. 8.2234 in my calculator. Next, use a linear approximation to estimate the value of sine 59 degree times tension 45 degree, tension 47 degree. So first step, you find a function in this format first. So I guess my f of sy will be sine x times tension y. Then next, guess a value for x and y that's close to these two numbers, but it's easier to be solved. I can guess my a is 60 degree pi over 3. I can guess my b to be, say, 45 degree. That's pi over 4. If I guess my a to be pi over 3, that's easy to be solved. If I guess my b to be pi over 4, it's easier to be solved. Next, we find f of ab. F of pi over 3 comma pi over 4. If I substitute pi over 3, pi over 4, I have sine pi over 3 times tension pi over 4. Then solve it. Sine pi over 3 is radical 3 over 2. Tension pi over 4 is 1, which is multiplied together, I get radical 3 over 2. Next, I find the partial derivatives. F sub x, take derivative with respect to x. I have cosine x times tension y. Then substitute a and b. I have cosine pi over 3 times tension pi over 4. Cosine pi over 3 is a half. Tension pi over 3 is 1. Half times 1 is half. And next, for f sub y, I take partial derivative with respect to y. I have sine x times secant square y. So substitute, I get sine pi over 3 times secant pi over 4 square. Sine pi over 3 is radical 3 over 2. Secant is the reciprocal of cosine. Cosine pi over 2 is 1 over radical 2. So secant pi over 4 will be radical 2. Radical 2 squared is 2. So cancel 2, I get radical 3. Next, find the linear approximation. L of sy is f of ab, which is radical 3 over 2. F of ab plus f sub x times x minus a plus f sub y times x minus y minus b. Then, when we try to approximate sine 59 degree, tension 45 degree, I plug in 59 and 47 degree. But remember, we can't plug in degree. You need to plug in radian measures. You can't plug in degree measure when you plug in. You need to plug in radian measure. 59 degree, if I convert to radian, multiplied by pi over 180 degree, it will be 59 pi over 180. And same thing for 47 degree, multiplied by 180 pi over 180, it will be 47 over 180 times pi. Then plug in 59 over 180 pi, comma 47 over 180 pi. I have radical 3 over 2 plus half times 59 pi over 180 minus pi over 3 plus radical 3 times 49 pi over 180 minus pi over 4. Then simplify, we have radical 3 over 2 plus half times, if you subtract, you get negative pi over 180 plus radical 3 times, sorry, that should be 47 pi. Radical 3 times 2 pi over 180. Then use calculator for the rest. I got 0.9178. Next, we will study differentiability. Let f be a two-variable function. We say f is differentiable at a, b if there exists epsilon 1 and epsilon 2 such that f of sy minus f of a b equal f sub x of a comma b times x minus a plus f sub y of a comma b times y minus b plus epsilon 1 of s comma y times x minus a plus epsilon 2 of x comma y times y minus b, where epsilon 1 and epsilon 2 approach to 0 as x, y approach to a, b. Here, epsilon 1, epsilon 2, they are functions of x and y. Observe this definition first, especially this equation. You see that this part is almost the same as the linear approximation, equation of the tangent plane. And when s and y very close to AB, when sy very close to AB, epsilon 1, epsilon 2 will be very close to 0. So this part will be very close to 0. This part will be very close to 0. That means if we zoom in toward the point AB, then in a very small neighborhood, for all s and y very close to AB, in a very small neighborhood, if the function gets very close to its tangent line, if in a very small neighborhood the function gets very close to its tangent line, then we say this function is differentiable. That means if a function is differentiable, it has a very good linear approximation near the point AB. Next, let's do some simple example about differentiability. Let f of sy equal to s cubed y squared. Show that f is differentiable at the point 1, 2. Show that f is differentiable at point 1, 2. Now, use definition. We first of all compute the partial derivative at 1, 2. We first of all compute the partial derivative at 1, 2. Then we try to find epsilon 1, epsilon 2. So f sub x of, let's try to find f sub x first. If I take partial derivative with respect to x, I have 3x squared y squared. If I substitute 1, 2, I have 3 times 1 squared, 2 squared. That's 12. For f sub y, I have 2s cubed times y. I take partial derivative with respect to y. Then plug in the point, plug in 1 for x, 2 for y. I have 2 times 1 cubed times 2, which is 4. Next, we compute f of sy minus f of ab. Let's compute f of ab first. Here our ab is 1, 2. Substitute 1 for x, 2 for y. I get 4. Then compute this. F of sy minus f of 1, 2. We have s cubed y squared minus 4 equal to f sub x of AB is 12. S minus A is 1 plus f sub y of AB. F sub y of AB is 4 times y minus B. B is 2. We try to find epsilon 1 times x minus A plus epsilon 2 times y minus 2. Next, I try to find s epsilon 1 and epsilon 2. Let's satisfy this equation. So what I can do here is look at the left side first. Left side, I have 12s minus 1, epsilon 1 s minus 1. If I factor, I can make 12 minus epsilon 1 times s minus 1. The other part is 4 plus y squared epsilon 2 plus y squared. If I factor, I have, that should be 12 plus epsilon 1. We have 4 plus epsilon 2 times y minus 2. How do we simplify the left side? Left side looks hard to simplify, but if I plug in 1 for x, I have y squared, 1y squared, which is y squared. If I plug in 1 for x, I have y squared. So I can write this as s cubed y squared minus y squared plus y squared minus 4. Then factor by grouping. I have s cubed, I can pull out y squared. I have y squared times s cubed minus 1 plus y plus 2, y minus 2 equal to 12 plus epsilon 1 x minus 1 plus 4 plus epsilon 2 y minus 2. Y squared times s cubed minus 1. S cubed minus 1 can be factored. S minus 1 times x squared plus x plus 1. So if I try to match the first term with the first term, they both contains x minus 1. So my epsilon 1. So if I try to match the first term with first term, s minus 1 is the same. So y squared times x squared plus x plus 1 must be the same as 12 plus epsilon 1 if you compare this term with this term. X minus 1 is the same. So y squared x squared plus x squared plus x plus 1 must be the same as 12 plus s1. If you compare the second term, if you try to match the second term, that should be y minus 2. Y minus 2 and y minus 2 is the same. So y plus 2 must be the same as 4 plus epsilon over 2 if I match these two terms here. Y minus 2 is the same. So y plus 2 must be the same as 4 plus epsilon 2. Then solve the first equation for epsilon 1. I have y squared x squared plus x plus 1 minus 12. My epsilon 2 is y minus 2. Now let's take a limit. Take a limit as x and y approach to AB. Let's take a limit. Let's take a limit as sy approach to AB. Our AB is 1, 2. When s and y approach to 1, 2, if I plug in 1 for x, I have, let me write it in a different piece of paper. When I take a limit as x and y approach to 1, 2, epsilon 1 is the same as limit as y approach to 1, 2, y squared x squared plus x plus 1 minus 12. Then I substitute 1 for x, 2 for y. I have 4 times 1 plus 1 plus 1 minus 12, which is 0. So as sy approach to 1, 2, epsilon 1 is 0. Take the other limit. Limit as sy. Limit as sy approach to 1, 2. Epsilon 2 is the limit sy approach to 1, 2. Y minus 2. So I substitute 2 for y. Substitute 2 for y. I get 2 minus 2, which is also 0. So as sy approach to AB, epsilon 1, epsilon 2 approach to 0. Therefore, f is differentiable. At the point 1, 2. Next example, let f of sy equal to 1 over 1 plus x plus y. Show that f of sy is differentiable at the point 0, 0. Show that this function is differentiable at point 0, 0. So let me write down the formula first. The formula to test for differentiability is f of sy minus f of a b equal to f sub x of a b s minus a plus f sub y of a b y minus b plus epsilon 1 s minus a plus epsilon 2 y minus b. If the function is differentiable as sy approach to AB, epsilon 1, epsilon 2 must both approach to 0. So let's compute f of AB first. F of 0, 0 is, I plug in 0, I get 1 over 1 plus 0 equal to 1. Then we find f sub x. When we find f sub x, we use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over the bottom square. It's negative 1 over 1 plus x plus y squared. If I substitute 0, 0, I get negative 1. Then for f sub y of 0, 0, let's find the partial derivative first. For f sub y of 0, 0, let's find the partial derivative first and plug in 0, 0. Again, use quotient rule. I get the same thing, negative 1 over 1 plus x plus y squared. If I substitute 0, 0, I also get negative 1. That's the partial derivative. Next, plug everything into this formula, then try to find epsilon 1, epsilon 2. My f of sy is 1 over 1 plus x plus y minus f of 0, 0 is 1 equal to f sub x times x minus a 0 plus f sub y. F sub y is also negative 1 times y minus b is 0 plus epsilon 1 times x minus a 0 plus epsilon 2 times y minus b is also 0. Then we try to let me simplify the right side first. Right side, if I simplify, I can write it as negative 1 negative x, negative 1x minus 1 times y plus epsilon times x plus epsilon 1 times x, epsilon 2 times y. I can factor like this: negative 1 plus epsilon 1 times x plus negative 1 plus epsilon 2 times y. That's the best we can do on the right side. Now let's simplify the left side. What can we do on the left side? On the left side, I can try to find common denominator first. 1 plus x plus y. Find common denominator, I get 1 minus 1 plus x plus y. Find common denominator, combine two terms together. Then 1 can cancel. 1 can cancel. I have negative x minus y over 1 plus x plus y. That's my left side. Try to match left side and right side. Looks hard, right? Doesn't look easy. So on the left side, what I can do is I can write it as negative x over 1 plus x plus y plus negative y over 1 plus x plus y. Then I try to write x and y by itself. I can write it as negative 1 over 1 plus x plus y times x plus negative 1 over 1 plus x plus y times y. Then bring it down. Negative 1 plus epsilon 1 x plus negative 1 plus epsilon 2 times y. Then if we try to match left side and right side, if I try to match left side and right side, I can see that negative 1 over 1 plus x plus y equal to negative 1 plus epsilon 1. So epsilon 1 equal to 1 minus 1 over 1 plus x plus y. Move this 1 over, become positive 1. Same thing for the other term. Negative 1 plus x plus y. Equal to negative 1 plus epsilon 2. Epsilon 2 is, I bring 1 over. 1 minus 1 over 1 plus x plus y. Then take a limit. We find epsilon 1, epsilon 2. If I take a limit as sy approach to 0, 0, we can clearly see that for epsilon 1, epsilon 2, they are exactly the same function. If I take a limit 1 plus x plus y, if I substitute 0 for x, substitute 0 for y, I get 1 minus 1, which is 0. So as sy approach to 0, 0, both epsilon 1 and epsilon 2 approach to 0. Therefore, f is differentiable. Therefore, f is differentiable. Next example, let f of sy be a piecewise defined function equal to s cubed times y minus x times y cubed over x squared plus y squared if sy doesn't equal to 0, 0 and equal to 0 if sy equal to 0, 0. Show that show that f of sy is differentiable at 0, 0. Show that f of sy is differentiable at 0, 0. So again, use the formula f of sy minus f of a b equal to f sub x of a b s minus a plus f sub y of a b y minus b plus epsilon 1 s minus a plus epsilon 2 y minus b. Let's find f of ab, fs of ab, f sub y of ab first. So let's find f0, 0 first. f0, 0, where sy equal to 0, 0, f of sy is 0. Next, we try to find f sub x of ab, f sub y of ab, f sub x of 0, 0, f sub y of 0, 0. This example was an old example I did last class. This is an old example I did last class. So last class we compute. Check your last class notes. Last class we compute f sub x of 0, 0 is 0. And f sub y of 0, 0 is also 0. Check your notes from last class. Both partial derivatives are 0, 0, are 0 at the point 0, 0. Then try to match the formula here. F of sy. When sy is approaching to ab, is approaching to 0, 0, sy is not 0, 0. So I use the first function. When sy is approaching to ab, sy is not the same as ab. So when sy is approaching to 0, sy is not 0, 0. I use the first function. For f of sy, I use the first function. X to the power 3y minus x, y to the power 3 over x squared plus y squared minus 0. Equal to f sub s of ab is 0. S minus a is 0. F sub y of ab is 0. Y minus b is 0. Plus epsilon 1 times x minus 0 plus epsilon 2 times y minus 0. If we simplify the right side, that's 0, I have epsilon 1 times x plus epsilon 2 times y. The left side I can rewrite in split this as two terms. I can split the numerator, write it in two terms. S cubed y over x squared plus y squared minus xy cubed over x squared plus y squared. For the first term, I can write y by itself. Write it as s cubed over s squared plus y squared times y. Second term, I can write x by itself. Y cubed plus x squared over s squared plus y squared times x equal to epsilon 1x plus epsilon 2y. If we try to match left side and right side, I can see that my epsilon 1 is s cubed over s squared plus y squared. My epsilon 2 is negative y cubed over s squared plus y squared. Then take a limit as sy approaches to 0, 0. we try to show both limit is 0. We try to show both limit is 0. So you can try to use epsilon delta proof to show that both limit is 0. Here I use epsilon delta proof, show that first limit is 0. You can pause the video and see the detail later. Here I use epsilon delta proof, show that the first limit is 0. Proof for the second limit is very similar. They are almost the same. So if you can also use a similar epsilon delta proof to show that it's 0. So when sy approach to 0, 0, both epsilon 1, epsilon 2 approach to 0. Therefore, f of sy is differentiable at 0, 0. As you see, using the definition of differentiability to show a function is differentiable, that's very hard. And to make your life easier, there's a theorem in the book that makes the problem much easier. There's a theorem in the book. It says, let f be a two-variable function if f sub x and f sub y both exist near the point A, B, and f sub x and f sub y are continuous at AB, then f is differentiable at the point A, B. This theorem will make your life this theorem will make your life much easier. Look at the following example. Let f of sy equal to e to the power of sy. Show that f is differentiable at the point 1, 2. If you try to prove it using definition of differentiation, it's gonna be very hard. You can try, it's gonna be very hard. If we use this theorem, it'll be much easier. We first of all find the partial derivative first. F sub x is exy times y. This is y exy. If I substitute 1, 2, I have 2e squared. F sub y is exy times x, which is x times esy. If I substitute the points 1, 2, I have e squared. So check the condition. F sub x, f sub y exists near the point 1, 2. And f sub x, f sub y are continuous. Exponential function times polynomial is always continuous. Exponential function and polynomial are continuous function. When you multiply continuous function, answer is continuous. So they are both continuous. So f sub x, f sub y exists near the point 1, 2. And f sub x, f sub y, they are both continuous. So by the theorem. f is differentiable at the point 1, 2. Using the theorem, it will be much easier. Next, we'll study differentials. dx, dy, dz, they are called differentials. In your first semester calculus, dy represents the change of the y value in the tension line as x changed. So we find dy using equation of tension line. We find dy using equation of tension line. Equation of tension line is y minus y0 equal to the derivative times x minus x0. The y minus y0 is the change of the y value in the tension line. X minus x0 is the change of x. F prime of x is the derivative. That's how we find dy for a single variable function. Then similarly, for a multi-variable function, for two variable function, dz represents the change of the z value in the tension plane as x and y changed. So we try to find dz using the equation of tension plane. Equation of tension plane is z minus z0 equal to f sub x of x0, y0, x minus x0 plus f sub y of x0, y0 times y minus y0. So z minus z0 is change of z. X minus x0 is change of x. Y minus y0 is change of y. F sub x, that's the partial derivative. F sub y stays the same. Similarly, for three variable function, say w equal to f of s, y, z. For a three variable function, we define the differential in a very similar way. So we say dw is f sub x of s, y, z dx plus f sub y of f x, y, z times dy plus f sub z of s, y, z times dz. That's dw for for three variable function. And for notation, sometimes we write dz as delta f over delta x times dx plus delta f over delta y times dy. That's another way to write differential. And similarly, for dw, sometimes we write delta f delta x dx, delta f delta y dy, delta f delta z dz. That's another way to write dw. They are the same. These two expressions is exactly the same. And for these two expressions, dz and dw is called the total differential. They are called the total differential. They are also called the total differential. dz and dw, they are also called the total differential. Let's look at a simple example first. Let z equal to f of sy. Let equal to x squared plus 3sy minus y squared. Part A. Find the differential. dz. Part B, if the point sy moves from the point 2, 3 to the point 2.05 and 2.96, find dz and delta z. Here, what's the difference between dz and delta d and delta z? dz is an approximate change in the tension plane. Delta z is the actual change in the function. Delta z is the actual change in the function. dz is an approximate change in the tension plane. Delta z is the actual change in the function. Let me show you step by step. Let's do part A first. So for part A, dz is df over dx, or f sub x, times dx plus f sub y times dy. We find f sub x and f sub y and plug in. That's my dz. F sub x, I take partial derivative with respect to x. I have 2x plus 3y times dx. And for f sub y, I take partial derivative with respect to y. I have 3x minus 2y times dy. That's my f sub x. That's my f sub y. That's the differential. Now part B. When x moves from 2, 3 to the point 2.05 and 2.96, change of x change from 2 to 2.05. So change of x is 0.05. Change of y move from 3 to 2.96. Y move from 3 to 2.96. So change of y is negative 0.04. Y value is going down, so that's why it's negative. So for dz, we plug in the values. 2x plus 3y. For x and y, we plug in the initial value. For x and y, plug in the initial value. I have 2 times 2 plus 3 times 3 times dx plus 3 times x minus 2 times y. Plug in the initial point. 3 times 2 minus 2 times 3 times dy. Change of y is negative 0.04. Let me continue on a different piece of paper. So my dz is 2 times 2 plus 3 times 3, that's 4 plus 9 times 0.05. 2 times 3 is 6. 3 times 2 is also 6. I get 0 times negative 0.04, which is 13 times 0.05 equal to 0.65. That's dz. Now for delta z, that's an actual change. You plug in the final point, plug in initial point, and subtract. The final point is 2.05 comma 2.96 minus the initial point f of 2 comma 3. You plug in 2.05 and 2.96 into the original function, get a value, put it here. Then you plug in 2, 3 into the original function, get a value, put it here, and subtract. I use calculator. I find f of 2.05 comma 2.96 is 13.6 0.6449. When I plug in 2 and 3 to the original function, I get 13. So subtract, I have 0.6449. So delta z represents the actual change from the point 2.2, 3 to 2.05, 2.96. Delta z represents the actual change. dz is an approximate change. That's a change in the tension plane. That's an approximate change between these 2 points. And delta z is the actual answer, but you can see that it's very hard to calculate. dz usually is easier to calculate. That's an approximation. Usually it's easier to calculate. That's the purpose we're using dz to do calculation. That answer is very close, but calculate dz is much easier than calculate delta z. Next, a right triangle is measured and 2 legs are found to be 3 inches and 4 inches. If the possible error in measurement are 0.05 inch, estimate the largest possible error in the computation of area and perimeter. So here we try to estimate the largest error. We can try to use differential to estimate the largest possible error. So use differential here. First of all, let's estimate the largest possible error for area. Suppose we have a right triangle. We know two legs are measured to be 3 and 4 inches. Let's call the first leg x, call the second leg y. This is a right triangle. Area of triangle is base times height. So area of this right triangle is base times height. Half of base times height. Half of x times y. That's the area of the triangle, of this triangle. Then we try to use differential to estimate the largest possible error. dA will be delta A over delta x times dx plus delta A times delta y times dy. So let's find each of them. First of all, delta A over delta x, that's the partial derivative with respect to x, which is half of y. And y is 4. If I plug in 4 for y, I get half times 4 equal to 2. And if I'm looking for the delta A over delta y, take partial derivative with respect to y, I get half of x. That's half times x is 3. Half times 3, that's 3 over 2. And dx, the change of x, largest possible error is 0.05. So change of x is 0.05. Change of y is also 0.05. Then plug in, we can find dA. Plug in, I have 2 times 0.05 plus 3 times 0.05 times 3 over 2 times 0.05. Then use your calculator. I get 0.175 inches, square inches. 0.175 square inches. That's the largest possible error in computation of area. Next, we try to find perimeter. Perimeter is the sum of all 3 sides. We know 2 legs are x and y. For the other side, we can use Pythagorean theorem. The other side is x squared plus y squared. So the perimeter is x plus y plus square root of x squared plus y squared. Then we try to estimate the largest possible error. We find the differentials. dp equal to delta p over delta x dx plus delta p over delta y times dy. Let's compute each of them individually. Delta p over delta x. I take partial derivative with respect to x. I get 1 plus half s squared plus y squared raised to negative half, and by chain rule times 2x. I plug in 3 for x, plug in 4 for y. I have 1 plus half times 1 over 5 times 2 times x, x is 3. Cancel 2. I get 3/5 plus 1, which is 8/5. Next, let's compute delta p over delta y. That's very similar. I take partial derivative with respect to y. I get 1 plus y, 1 plus half of x squared plus y squared raised to negative half times 2y. Then substitute, plug in 3 for x, plug in 4 for y. I have 1 plus half times 1/5 times 2 times y, y is 4. Cancel 2 here. I get 1 plus 4/5. 1 plus 4/5 is 9/5. Then we know dx is 0.05. dy is also 0.05. Then we plug in. That's my dp. Delta p over delta x is a over 5. dx is 0.05. Delta p over delta y is 9 over 5. And dy is 0.05. Then use calculator. I get 0.17 inches. Next problem. The base radius and the height of a right circular cone are measured as 10 cm and 25 cm respectively. If the largest error in measurement is 1%, estimate the largest possible error and the largest percentage error in computing the volume. So this is a right circular cone. Volume of a cone, the formula is 1/3 pi r squared h. That's the volume of a cone. We are looking for the largest possible error and the largest percentage error. Let's find the largest possible error first using differential. So dv, use differential, dv equal to delta v delta r times dr. There are two variables, r and h. Delta v over delta r times dr plus delta v over delta h times dh. There are two variables, r and h. So find the differentials first. The dv is called a total differential. Find the total differential first. Then we find the partial derivatives. dv over dr. I take derivative with respect to r, I get, bring 2 to the front, I get 2/3 pi rh. I get 2/3 pi rh. Then I substitute, plug in 10 for r, plug in 25 for h. It's 2/3 pi r. R is 10. H is 25. 2 times 25 is 50. 50 times 10 is 500. I get 500 over 3 pi. Then next, I find the delta V over delta H. I take partial derivative with respect to H. I get 1/3 pi r squared. Then I substitute. R is 10. Substitute 10 for r. 10 squared is 100. 100 times 1/3 is 100 over 3. Pi. And next we find the r. The largest possible error in measurement is 1%. Radius is 10 centimeter. We are looking for 1% of 10 centimeter. Largest possible error is 1%. Radius is 10 centimeter. We are looking for 1% of 10 centimeter. So I take 10 times 1%. 1% is 0.01. 10 times 0.01 is 0.1. So radius, check, dr is 0.1. dh is also 1%. The largest possible error for the height is also 1%. Height is 25. So we take 25 multiplied by 1%. 1% is 0.01. 0.01 times 25 is 0.25. Then we plug in. dV over dr is 500 over 3 pi. dr is 0.1. Delta V over delta H is 100 over 3 pi. dH is 0.25. Then use your calculator for the rest. dV equal to 25 pi cube centimeter. Next, we are looking for the largest percentage error. Formula for the largest percentage error is dV over V. That's the formula for the largest percentage error. So let's find V first. V is the volume. Formula is here. 1/3 pi r squared h. R is 10. H is 25. Multiply out, we have 2500 over 3 times pi. Then we use dV over V. Use dV over V. 25 pi over 2500 over 3 pi. Cancel pi from top and the bottom. When we divide, keep the top, flip the bottom over. We get 3 over 100. That's 3%. So the largest possible percentage error is 3%. That's the largest possible error. That's the largest possible percentage error.